Om Shri Sai Ram. With humble pranams at Swami's lotus feet, myself Devaharsha. As part of the Modern Optics course, my topic for the seminar is Optical Lithography, making submicrostructures using optical beams. The main objectives of this seminar are to learn what is optical lithography, to know its various applications, and to understand the basic principle and the basic process behind it, and also to know the different types of lithography systems, their limitations, and different methods to improve the lithography process. And we also want to look at what is the current state of the technology and what are we aiming at in our future. In the end, we also we have a quick glimpse of what other techniques are there which are related to this optical lithography. So what is this optical lithography? Going into the formal definition, optical lithography, also called as photolithography, is a process used in microfabrication to pattern parts on a thin film or the bulk of a substrate. It uses light to transfer a geometric pattern from a photomask to a chemical photoresist on the substrate. So the keywords are substrate, photomask, and the photoresist. I will come to these keywords in a subsequent part of my seminar. So what are its important applications? Why do you actually need to study this kind of a technique? This technique is most widely used in the process in high volume manufacturing of nanoelectronics by the semiconductor industry. If we look back at the history, this optical lithography process was developed for the manufacturing of IC chips. In our homes, all our laptops, computers, smartphones, smartwatches, every smart device that we are using is a resultant of this VLSI technology. This VLSI stands for very large scale integration, and we also have ultra large scale integration. As we can see in the image, the chip is present on the human fingernail. Its size is even small compared to the size of a human fingernail. So we are aiming at such high end technology. So this is what is the main important application of the lithography process. So what is the basic principle behind it? So in our homes, we have windows or grills. So at around 10 o'clock or 11 o'clock in the morning, we have sunlight falling on the windows, and the shadow of the window falls on the floor below it or on the wall opposite to it. So this is the basic principle behind the working of a lithography process. So in the lithography process also, we have a patterned mask which is exposed to the UV light, and the UV light which passes through the mask will react with a photosensitive layer, and this photosensitive layer will be later developed to give rise to a pattern, and into this pattern we fill copper or any other metal to get what is known as a printed circuit board. So here we can think that this green layer which is present in the printed circuit board to be substrate, and these copper lines are the metal which are using in our circuits. So this is the basic circuit of the PCB. So as we can see here, we have a mask which is exposed to the UV light, and using a series of reduction optics, we print the miniature version of the circuit on the wafer layer. So this is the ray diagram of how this lithography system works. So we have a light source, and this passes through condenser pupil, and we have a condenser lens, mask, and the projection lens. Here we are representing using a single lens, but in reality this condenser lens and projection lens are a series of complex optics. The light which passes through this series of optics will fall on this photoresist, react with it, and then result in the printing of the IC chips. So now let us go little more deeper into what the basic process is. So the first step in the process is to prepare our wafer. Our wafer consists of two things. First one is a substrate, second one is the metal oxide layer. It could also be a semiconductor p-type layer. So how do we prepare this substrate? So this substrate we might store for a long time, the green colored board. So we need to chemically treat the substrate to remove all the contaminants, and then we bake the substrate to a temperature of around 110 degrees centigrade to remove any moisture which is present after the chemical treatment. Then we paste the oxide layer onto the substrate. This oxide layer is a complete sheet. We are pasting it onto the substrate. At the end, what we aim is to remove the parts which are not required for us, and what is left behind on the substrate is our circuit. So that is what we are aiming at. So the next step in our process is to apply the photoresist. This photoresist plays the crucial role in the process of this lithography. It is a simple chemical which has certain properties. So how do we apply this photoresist? This photoresist, before applying it, we need to apply a water repellent layer on the SiO2 layer, and after which we apply the adhesion promoter. So we apply this water repellent so that adhesion of this photoresist layer happens firmly to the oxide layer. And the process of applying this photoresist is called spin coating. So what is a spin coating? In the process of spin coating, we have a wafer layer and we dispense our photoresist chemical onto the wafer, and this wafer is spun at a certain speed to achieve the desired thickness and uniformity. And then later we soft bake it to around 70 to 80 degrees centigrade to lock the thickness and the uniformity, to make it rigid to up to certain extent. So the next process is to align the photomask. In the process of aligning photomask, we firstly need to prepare this photomask. So how do we prepare it? The photomask consists glass as a substrate. In general, we use quartz, and then we print our chromium metal based circuit onto this glass. This preparing photomask is also another lithography process, but the difference is this lithography process need not be complicated because the size of the mask is comparatively larger to the size of the chip that we require. So a simple computerized printing can do it. So the printing process we use is using a laser beam or an electron beam. So we need to carefully align this photomask. It has to be exactly parallel to the photoresist layer. Improper alignment or some tilt in the alignment of the photomask will lead to what is known as overlay errors. This is the place where human errors can induce. We need to take care of this step very carefully. So the next step is to expose the mask to the UV light. So wherever we do not have chromium, the UV light is passed. Wherever we have the chromium, the UV light is blocked. So wherever the photoresist material is exposed, this UV light reacts chemically with the photoresist material. The next step is to develop and remove the photoresist which is exposed to UV light. Because the photoresist has been chemically altered in the place where it is exposed, we can use a solution what is known as a developer solution and remove the part which has been exposed to the UV light. Now, depending on the combination of this photoresist material and the developer solution, we get two types of photoresist known as positive and a negative photoresist. After exposing it to UV light, if we clean away the part which has reacted to the UV light, it's called positive photoresist. But in contrary, if we clean away the part which has not been exposed to the UV light, it's called negative photoresist. Whatever has been reacted is left behind, and the names positive and negative are self-explanatory. As in the case of positive, wherever we have a hole in the mask, we have a hole in the photoresist. In case of a negative photoresist, wherever we have a hole, we have a substrate, and wherever we have a mask, we have a hole, and hence the names are given. So after developing it, we hard bake it to make it even more rigid and adhere strictly to the substrate layer. So the next step is to etch the exposed oxide. So now that we have certain parts of the oxide layer being exposed, we fill a chemical known as etching agent. So this removes only the part which is exposed. So whichever is just below the photoresist layer and not exposed to the chemical will not be altered at all. So this is the process which removes the unwanted material from our oxide layer. So the next step is to remove this unwanted photoresist layer. So we use a material what is known as resist stripper solution. So in the end, what we get is a substrate, the green colored PCB, with the oxide layer in the form of a circuit. So essentially, what we are printing on chromium is our circuit itself in a bigger form, and what we get on the substrate is a circuit in a smaller form with a metal, using a metal lines or a semiconductor. In case of a semiconductor, here instead of using a chemical agent to etch it, we dope it. If the oxide layer was completely p-type semiconductor, we dope this part using an n-type conductor, so that we get the entire semiconductor layer becomes a n-type p-type combinations of transistors and resistors. So now we will be better able to understand our diagrams. So the basic process is exposing the mask to the UV light, and then this patterned mask transfers through a series of optics, reduction optics, and then prints onto the wafer surface. A miniaturized version is printed onto the wafer surface. So this is the basic process. So now let us go into the different optical lithographic systems. So first one is the contact printing. As the name suggests, in contact printing, the mask layer and the photoresist layer are in contact with each other. It does not provide any reduction. It is only 1:1 magnification. But its advantages are, its cost of printing is very less. It provides us a moderately high resolution. But few disadvantages. Because of the contact between the mask and the photoresist layer, it might degrade both the mask and the semiconductor or the silicon dioxide layer, which is not desirable. So to overcome these disadvantages, we devised what is known as proximity printing. In this as is shown in the figure, we just introduce a small gap between the mask layer and the photoresist layer. Even this does not provide any demagnification. Only 1:1 magnification is provided. Its advantages are, it's obvious that there is no degradation of mask or the photoresist layer. It has lesser cost, but it provides a slightly lesser resolution. Its main disadvantages are, because of the gap introduced, we might have the near field diffraction effects and interference pattern effects coming into the place. Because of this, our accuracy is limited, and hence we have lesser repeatability. The next method is projection printing. This projection printing is the most widely used process in the industry currently. Although the current technique is slightly different from the diagram shown here, the basic principle used is this projection. The most valued advantage of this projection printing is the reduction in size, the demagnification. The miniaturization of the circuit happens here in this projection printing. As we can see here, the size of the mask is bigger in size. We use a projection optics which reduces the pattern by 200 times and then print it onto a wafer layer. It provides a very high resolution, absolutely no degradation of masks. It provides a high repeatability. And disadvantages are, it's extremely expensive and the equipment is very complicated. The lens that are involved in this process are very complicated. And as usual, the diffraction and interference effects limits our accuracy. So what is this diffraction effects? Why is this coming into this picture? So if we look at our windows or grills in our homes, the size of the slit in the window is around few centimeters, but the wavelength of the source, the sunlight, is around nanometers. So the difference is large. So we do not have any diffraction or interference effects coming into the picture. But in case of this projection printing, the slit width of the lines present in the mask and the wavelength of the source used are comparable to each other, because of which these diffraction effects come into the picture. We need to overcome these limits. So what are the limitations of this lithographic process? The performance of a lithography system is characterized by the three major parameters. First one is the resolution. Second one is the depth of focus, also known as DOF. Third one is the overlay accuracy. Resolution. Resolution is diffraction limited. The optical projection systems used today use very complex lenses. The multi-element lenses that correct for virtually all of the common aberrations, they operate at diffraction limit. As patterns approach the same order of the magnitude as the wavelength of light, we must be concerned with the wave-like nature of light. So diffraction limit is lambda by 2. We cannot have slits whose slit width is less than lambda by 2 in the masks. And the resolution is defined by the Rayleigh's criteria. And as usual, in the Rayleigh's criteria, the terms are lambda being representing the wavelength and Na representing the numerical aperture. We have one more parameter known as depth of focus. So while we try to increase the resolution, which results in smaller patterns, it also affects the depth of focus. It's given by K2 into lambda by Na square. Although K1 and K2 are given different indices, for one set of instrument, so for the given instrument, the value of the K1 and K2 are taken to be same. So what is this K1 and K2? I'll just explain this next slide. So when we try to increase the resolution, we are increasing the numerical aperture, because of which the value of the depth of focus also reduces, which is not desirable. We need higher resolution as well as higher depth of focus. That's what we need. The next one is the overlay accuracy. So as I mentioned earlier, the alignment of the mask to the underlying layer is also very important. It must not be tilted. It must be aligned parallelly to the surface. This introduces some errors. We need to overcome these errors. So while overcoming all these limitations, we need to keep the cost effectiveness in our mind. Just because we need to improve our technique, it doesn't mean that we use costlier equipment to improve our accuracy. It defies our purpose. Our main purpose is to manufacture VLSI chips using lesser costs. So that is our actual aim. So as I have mentioned, for higher resolutions, that means for larger numerical apertures, we get a smaller depth of focus. The depth of focus is smaller. But for smaller resolutions, the depth of focus is large. What we need is a large depth of focus and a large resolution. We need to strike a balance between both the resolution and the depth of focus. So how do we do that? So what is the depth of focus? As we can see here in the image, a high resolution or a small depth of field lithography can focus only on point A or point B, but not on point A and point B simultaneously. So that's the reason why we need the photoresist layer to be extremely flat. The variations in the surface heights of a processed wafer must be less than the optical depth of the focus. Thus, for high resolution lithography, the surface must be planar. It must be flat in nature. So how do we improve our technique? So how do we overcome these limitations? So every couple of years, we need to improve our limitations while keeping cost in our control. So this is what reduces the size of a chip drastically. So we need to reduce our size from 90 nanometer lines to 22 nanometer lines. So how do we do that? We use this Rayleigh criteria. So what is the Rayleigh criteria? As I mentioned earlier, Rayleigh criteria is nothing but R is equal to K1 into lambda by Na. So what is this R? R is the smallest half pitch that can be printed. So what is this smallest half pitch? So as we can see in the diagram here, there are two copper lines which are printed just next to each other. So this is the maximum resolution that we can achieve. The distance between the center of the first copper line to the center of the next copper line is called as the pitch of the printing. And equivalently, the half pitch is nothing but half the distance of this pitch. It is defined by distance between the center of this green substrate line to the center of this copper line. It is called as the half pitch of our printing. So this half pitch actually is a measure of how closely the futures can be packed together. The next one is the K1. So what is this K1? K1 represents the collection of all factors that can be done to improve our resolution. So how do we improve our resolution? We need to reduce the value of K1 so that our smallest half pitch can be reduced. So we can print thinner and thinner lines. So how do we improve it? We use resolution enhancement techniques like off-axis illumination and phase shifting masks to lower the value of this K1. Next one is to equivalently reduce the value of this lambda, lower the value of wavelength. So today's tools use a 103 nanometer ARF excimer lasers in contrast to the 436 nanometer mercury lamps which are used earlier. So we are even trying to reduce the value of the wavelength of the source. The next one is to alternatively increase the value of numerical aperture. As we know, the numerical aperture depends on the refractive index of the imaging medium. Na is equal to n sin theta. So by increasing the refractive index of the imaging medium, we can improve the value of numerical aperture, thereby reducing the value of the smallest half pitch that can be printed. So this technique is called immersion lithography. So what is immersion lithography? Immersion lithography is an enhancement technique which replaces the usual air gap between the lens, final lens and the wafer layer with a liquid of higher refractive index. If the liquid we use is our water, for water at 193 nanometers it has a refractive index of 1.436. For the same numerical aperture, the immersion system has a better depth of focus than the dry system by at least the factor of the refractive index of this layer used. This immersion system will give us a better resolution system. In contrary to what we expect, it does not have a big drop in DOF, which is resultant of the complex optics which we design especially for the immersion system. So we will not have a big drop in the depth of focus. But how much can we go lower? How much can we improve our resolution? We have a certain limits. So today's best tools and process have evolved a lot, and the lambda has been reduced from 436 nanometer to 193 nanometer ARF excimer lasers, and the value of numerical aperture has grown from 0.5 to 1.35 using immersion lithography technology, and the K1 factor has been reduced from 0.7 and limited to 0.25. 0.25 is the lowest we can go using 2 beam imaging. So using all these values, the lowest half pitch that we can achieve is around 36 nanometers theoretically, but practically it is limited to around 38 to 40 nanometers, and hence the minimum pitch is around 75 to 80 nanometers. So this is the complex optics which have been used in the lithography system. They have evolved a lot from 1982 to 2004, and they have kept on evolving, and the optics which we use currently are even more complex. So this is the schematic of the entire lithography process, the machine which is present. So here we have a geometric photo mask which contains a geometric pattern which is exposed to the UV light, and the geometric pattern in the form of UV light passes through this series of complex projection optics which reduces the size and prints on this wafer. So this is the essential and the crux of the lithography process. So what is our current technology and what are we aiming at in our future? So this organization known as ITRS, International Technology Roadmap for Semiconductors, has published this roadmap in the year 2011. So in the year 2011 they were able to achieve a half pitch of 36 nanometers, and they were aiming to look at 11.3 nanometer half pitch by the year 2021. So this is what they were aiming at. So to lower the value of this half pitch, we also need to improve the wavelength of our sources, and this wavelength of our sources improved from 365 nanometers to 193 nanometers, and had continued to extreme ultraviolet regions of 157 nanometers and 135 nanometers. So this is what is our Moore's law, a famous Moore's law. What does it tell? It tells that the number of transistors that can fit into one single chip will double every 2 years, which means we have to print finer and finer lines on our PCBs. With finer and finer lines, we can fit more number of transistors and resistors or more complex circuits onto a smaller chip. So that is what is this Moore's law. It has been followed till date. So the same organization, ITRS, the 2.0 version of it, renamed as International Roadmap for Devices and Systems, it has published another roadmap in the year 2020. So by 2020 we had achieved a half pitch of 15 nanometers, and by the year 2028, in our near future, we are looking at 8 nanometer thin lines. So this is the vision that our industry has. So this is the complex system that we are aiming to build. So in conclusion, optical lithography process started with the IC fabrication. The earliest forms used cut and paste method using scissors to make our masks, but now we have evolved a lot. We use computerized printing systems to prepare these masks. We have gone a way ahead. We have reduction in wavelength, increase in the numerical aperture, and development of resolution enhancement techniques, which resulted in state-of-art machines which are able to perform lithography very well. And as we have seen, ULSI, ultra large scale integration, is result of this evolvement. So just to complete, so we learn another technique. So if we remember, in case of light microscopy, we are limited by the wavelength of the source. So we shifted to electron beams for imaging. Similarly here also, for the limitation which is posed by the microscopy technique, we use electron beams to achieve higher resolution, and this technique is called electron beam lithography. And these are the basic schematic diagrams used, and here the optics used are magnetic and electronic lens which control the size of the beam and produce a miniature version of our chip. So this is the technique which I want to discuss. So at the end, I would like to thank Bhagwan and Muthukumar sir for giving me this opportunity to present myself. Thank you. Jai Sai Ram.